our third and last speaker, who is Ethelbert Ezemobi from the Department of Aerospace and Mechanical Engineering. He will give us a speech entitled Prevention of Thermal Runaway Through Accurate SOH Estimation with Parallel Layer Extreme Learning Machine. Ethelbert received his bachelor degree in mechanical engineering from the Federal University of Technology in Owerri, Nigeria, in 2010, and a master's degree in mechatronics engineering at Politecnico di Torino. He is a PhD candidate at the Department of Mechanical and Aerospace Engineering at Politecnico, with ongoing research circled around artificial intelligence and energy management applications in automotive. As part of his program, he is currently serving as a visiting researcher at the Department of Mechanical and Mechatronics Engineering in University of Waterloo, Canada. And if I can add, he is also one of us. He is also part of the IEEE Student Branch organization committee, let's say. So thank you, Ethelbert, for your service, and we will enjoy your talk now.
Thank you very much for that introduction. Thank you also, viewers. I will be talking, as has been described, on prevention of thermal runaway through accurate state of health estimation with parallel layer extreme learning machine. I'll try to make this presentation very simple so that it will be relevant for both the specialist and non-specialist audience, which I perceive we have here. Let's start by giving some motivations why we want to do this work. In the recent years, EU has been very strategic.
I'm sorry, Ethelbert. I'm not sure whether you want to share something or not, because we are not seeing.
I am sharing my screen. Can you see my screen?
Not yet.
I'm sharing already. Okay. Okay. Can you see it now?
Yeah, I guess Yuri behind the scenes is managing it. Okay.
Can you see my screen?
Yes. Can you share the slides, actually?
Okay.
Okay. Perfect. Thank you.
Oh, sorry about that.
Oh, we lost it again.
Lost it?
Yeah.
I don't know what the problem is, really. To go back. Let me know if you can see it.
We see your desktop. I mean, I see your desktop. Can you put the slides on so we can put them
sure.
in the live? Okay. Okay.
Is it okay?
Yep.
Oh yeah. Thank you very much, and sorry for
no worries.
Interruption. So let's start by giving some motivation why we're having this discussion. In the recent year, EU has been very strategic in policy implementations to reach the goal of climate neutrality by 2050, as been proposed by EU and other major stakeholders. And interestingly, the idea is to continuously replace the billions of existing internal combustion engine vehicles, which contribute to about 87% of the global petroleum consumption and about 33% of the global energy. So replacing these, I think, will have a great impact in reaching that goal. Interestingly, the sales of electric vehicles from 2010 to 2019, as can be seen here, has been quite promising. And this reinforces the hope of reaching that goal. The truth is that no mission is said to be successful without stories of failures and pain points, and this isn't going to be an exception. Just in 2018, more than 16 cases of incidents are recorded. And these incidents are fire incidents associated with electric and hybrid vehicles. And you can agree with me that this scene is quite unpleasant. We don't want this. But sadly, this threat will continue to grow with increase in the demand of electric and hybrid vehicles, and as the need to increase the energy and the power density of the cells will grow. What is the problem? The root cause of this whole fire incident is the terminology, the phenomenon known as the thermal runaway. Normally, the battery is designed to work within state of charge or state level between 20% to 80%. Outside this zone, an uncontrolled application of the battery is very, very unsafe because of the rapid change in the voltage around that, outside that zone. Also, the temperature of the battery is increased with the current demand, current request in cells. As can be seen in this plot, with 7C being the highest current and 1C being the lowest current applied or requested from the battery. And there are high peak currents that are associated with electric and hybrid vehicles. These high peak currents set conditions in the cells, that drives the cell cumulatively with the condition on which the battery is being operated to a third level degradation of the battery. And at this point, the thermal runaway is inevitable. And usually the battery is set on fire. Now, let's dive into the details to understand what we need to do to solve this kind of problem. We'll talk about the state of health and how we can estimate it and what use it is for us. What you see here is a cylindrical cell that is usually common with many hybrid electric vehicle and electric vehicles. In every cell, you figure out that usually with aging of the battery, the inactive area tends to grow. This inactive area has to be monitored properly if you really want to know the actual state of charge of the battery. Because if it's not known, you have a fake information about the state of charge. Remember that you want to ensure that the battery is operated within the required zone of 20% to 80% state of charge. So accurate state of health estimation is very crucial for this. That's not all. The second problem is that the aging characteristics of the cells that have the same specification varies. It's not the same, even if they are subjected to the same load condition. This is simply because currently the chemical industry is not able to guarantee determinism in the chemical processes, especially in the lithium-ion cells. By the way, I would like to point out that I'm going to use cell and battery interchangeably. Where I need to talk about the group of cells or group of batteries, I will be specific with the term battery pack. The cell you see by the plot you see at the lower right is the degradation pattern of cells, 4 different cells of the same specification, 2 ampere hour capacity lithium-ion cells. And you can see that although these cells have the same specification and they are subject to the same load condition, yet the pattern of change of aging changes, over time. And this is really something that an algorithm that is chosen to estimate the state of health has to take care of. It has to be able to adapt to this change and still be able to accurately measure state of health in order to correctly predict the state of charge. And in a typical electric vehicle, we have hundreds and thousands of these cells put together. You can see how crucial it is that this algorithm has to be as adaptive as possible. Now, let's talk about the algorithm that we are going to present in this work. This is a parallel extreme learning machine. It's a parallel layer extreme learning machine, sorry. This is a tool that became a solution to, for me, a possible way of solving this kind of problem. Usually is with transfer learning, because these batteries, their behaviors are quite large. So you want to find a way to adapt the behavior of one battery to another. Usually this is solved with transfer learning. But this algorithm, as simple as it is still able to solve this problem. The building block of the PL-ELM is the ELM proper, that is the extreme learning machine. Each of the blocks you can see here, block 1 and 2 are the blocks of extreme learning machines, which is just a single layer feed-forward neural network. Now, when they combine together in this parallel mode, they build a stronger structure. The structure of this PLM is composed of the input layer, the hidden layer, and the output layer. The input to the model, to the architecture, is the feature variables that are believed to characterize the state of health which we are about to measure. So the inputs we're going to discuss in the following slides. It combines with the weights and biases. And these weights and biases are assigned deterministically, and they both pass through a nonlinear activation function. Here we use a sigmoid function, and this gives us a hidden layer matrix of H. Also, the same happens for the second block, second ELM, and then we combine two of them with element products of the two of the matrices to get H, which is the hidden layer matrix. We know the Y, which is the state of health which we intend to estimate, or the one we have, the measured state of health. Now, the only unknown is the output layer matrix, output layer weight, which is theta. And this theta is computed simply by the generalized Monpenrose inverse matrix of the hidden layer matrix H times the output measurement, which is Y. And once we have this output layer matrix defined, we're able to multiply it with the hidden layer matrix, which we already set with the deterministic weights and biases, and we can estimate the state of health here. So that's so simple. You know, the capacity, the nonlinear handling capacity of this model is associated with the fact that these two non-linearly activated blocks combine in a way that it's projected in the feature space to handle the problem in the most efficient way than a single ELM model will do. Now let's talk about the feature extractions. As you know, that the features are the inputs of the structure of that PL-ELM structure, and they are used for the training of the model. We have the privilege to have our data collection from the Prognostic Center of Excellence at NASA, and we use these data sets to train our model. The figure you see here on 1A is the characterization of state of health, and the features for this characterization are voltage, the state of charge, and the energy in watt-hour. You can see how the state of health changes in this arrow. So the aging is in the direction of the reverse arrow. The features are extracted by discrete variations of the state of charge, the voltage, and that of the energy. These things are put within, these features are put within, they are captured within a buffer of 90 seconds. Of course, it's variable, but we have chosen 90 seconds time length of buffer. yeah, for the best computation. And you can see here that the result is quite nice with a root mean square error of 0.046. We also show, and this is actually in the training phase, we show the error within distributed within 99% confidence level. And you can see here that all the errors lie within minus to plus 0.15. Then again, I forgot to mention that the structure of this algorithm is selected by varying the number of neurons. By varying the number, you can choose the more reliable, the more accurate model as you desire. So you can see from here, the 2C, that the model reached the stability at around 10. So, but we used only 12 neurons for designing our model. Now, in the prediction, since we have our model ready, the next is for us to use the model to predict the state of health on other batteries. So we used only one battery, which is battery number 7, to train the model. And now we use other batteries to validate it, the battery number 5, 6, and 18 to validate our model. And as it can be seen here, the model has shown to be very, very adaptable to the whole dynamics and predict the state of health very accurately for the rest of the batteries. And here we can see that the root mean square value is quite nice. I think the maximum there is 0.73. And we also have, you can see the error bound is quite little too. That's for the worst case scenario, we have between -62 to 1.31. Then a bit of comparison with just a single layer feed-forward neural network, which is the ELM, as I discussed earlier. You can see that this ELM doesn't have as much capability as in adapting to estimate to the changes in the state of health, and that gives us a lot of errors in prediction. Watch that number B, watch the figure number B there, and you figure out that the error bound is quite large, from 3.18 to 4.82, and the root mean square value of 1.563. Yeah, one interesting thing about this PL-ELM is that it actually, with a less model complexity, it's able to give a more accurate model results than ordinary ELM. I can tell you that with experience and with experiments, that even by increasing the complexity of the model for the ELM, we're not able to get a better result. So some benefits of this PL-ELM are quite simple, because you can see apparently what we do is just a least square to obtain the output metrics. Quite simple, and very, very fast, very, very computational efficient. At the end of that, when the model is trained, of course, also very fast. We can predict state of health just in 93 microseconds. That's super nice, and that's why it's very suitable for online application, considering also the minimum space that it takes in the memory. Let's move on. So without letting you get lost in so much of the details, I would want to summarize this work and with a bigger picture so that we can understand what we want to achieve here. The goal is for us to measure state of charge accurately. And for us to do that, we will apply the model we have discussed in this work to predict state of health, even for different cells that exist. When we are able to predict the state of health, we use it to correct the state of charge. And if we can correct the state of charge and get the precise state of charge, we also need an information about the thermal condition of the battery. We use other algorithms that we developed also in the lab to predict the state of the temperature of the battery. And when these two algorithms are put together, they are all buckled into the BMS, the battery management system. And with that, you can guarantee a safe operation of the battery pack, of the entire battery pack. And this is what we want to achieve. Without using this model, we have a very high risk, potentially dangerous situation, because you can see that the risk impact with where the battery, the thermal abuse and the electric abuse is so high. And this is more reason why we have thermal runaway. But by controlling these appropriately, by accurately measuring the state of charge and using it state of health and using it to correct the state of health, we can move the electrical abuse from the state of the dangerous state to a relatively safe zone. The same also apply for the thermal abuse. And when we do this, we can enhance the safety in the use of our electric and hybrid vehicles, and also achieve the goals of EU and other major stakeholders of reaching climate neutrality by 2050. These are some of the work that we have published that may be relevant for you. If you might want to search on them, you can get them and download them and read them for more details. Yeah, they told me that working in the batteries are quite boring. I hope I didn't bore you, but really it saves life. So that's why we're doing it. Thank you very much for your audience. Thank you.
Thank you, Ethelbert. I mean, I guess it requires a lot of work to give a reliable estimation, and even if we don't perceive it in our daily life, I guess any electronic and any electric power device now needs this kind of work. So thanks a lot.
Thank you.
We have a few questions. Let's see. Apart from state of health, what are the other parameters which can be a good measure for the health of a battery?
Okay, for the what?
Alternatives? Apart from the state of health, as you described it, are there any other parameters that can be relevant metrics to characterize?
Okay, the health of the battery. Yes. Actually, there are different metrics that exist for measuring the battery aging. Yeah, some people just use capacity, of course. Yeah, and yeah, a couple of them out there in the literature, but the most pervasive, I would say, is the state of health. Of course, I don't know if it has been properly adopted, and but most people use it. Yeah. Okay,
I see. And finally, how would the algorithm you propose work in a practical application, and what are the limitations?
Okay, yeah. One, as how it can work in the application. Usually, what we experience is that in the charging phase of the battery, we can use like a constant current load, as can be seen that the experiment is conducted here with the constant current load condition. If this is the case, we can accurately estimate the state of health on the go. Yeah. What we do actually is when this algorithm is put in the BMS at that time slot of 90 seconds, which is the buffer length, we capture a discrete value of the feature variables, which we feed in an installed algorithm that has been trained, and with this, state of health is estimated online. So that's how it works. Then as for the limitation, this algorithm has not, like I said, it works very well if you just want to use it at the charging phase, which is quite common with electric vehicles that charge, that they just have to park the car and then they charge. But with dynamic profile, it's a bit difficult to estimate the state of health with this. We're still trying the classification algorithm that exploits also ELM because of the elegance and and computational efficient. So yeah, that's one of the limitations. Limitation is that it hasn't been proven so well for the dynamic load, but for the constant load, very, very fine. Thank you.
Okay, thanks for the very complete answer.